To simplify circuits that we're analyzing, we sometimes will find it helpful to make impedance blocks. Here we're going to group elements together and treat them as a single element, and we are going to find what we call their equivalent impedance. Impedance is kind of a generalization of resistance, where we can add up the impedances of the resistors, capacitors, and inductors that make up a group of elements. So here we have a circuit where we have the inductor and the resistor in series, and then it comes down and there's a capacitor, and we want to find the voltage across the capacitor here. It's a very simple example of what we might do. So what we can do is group together the inductor and the resistor as a single element, and we would say that it has an impedance of Z1. Now I need to calculate what impedance Z1 is. So here in series I have the inductor and the resistor. We're going to use the same series and parallel rules that we did for just resistors. So if they're in series, we are going to add their impedances together, and if they're in parallel, we're going to use the harmonic average. So for Z1, where they're in series, I'm going to add together their two impedances. So we see here, their resistor has impedance that is just the resistance, and an inductor has impedance of L times S, and then the capacitor is going to have an impedance of 1 over C times S. So it's basically, what are we multiplying the current by when we find the voltage drop? That's what the impedance is. So Z1 I can write as R plus LS. Now I can also make an impedance block for the capacitor. It isn't quite as useful in this example because it already is only one element, so simplifying it further doesn't really accomplish much, but I could say that that has an impedance of Z2. But in this case, Z2 is just 1 over CS. Again, that's what we would multiply the current by to find the voltage drop across this capacitor. So let's employ this in another example where we're trying to find a transfer function. In this example, we have a pretty simple circuit, but now we're trying to find the voltage across a resistor and a capacitor that are set in parallel. And then before we get to that element, we have another resistor. So we are looking to find here that output voltage over the source voltage, where again the output voltage is the voltage over the resistor and capacitor in parallel. So I'll put formally here, what are we trying to find? We want V0 over Vs, and we can call that our transfer function G. Now here, my diagram I'm going to make a little bit different than what we saw in previous examples where I basically just copied the same diagram over again. This is going to be a simplified version of the diagram because I'm going to employ an impedance block. So if we see here, this resistor and capacitor, I can simplify this by grouping them together and call it a single element that will be my impedance. And so I'm going to replace this and say that it has equivalent impedance of Z. Now, again, I could also turn R1 into an impedance block. I'm not going to do that in this case. It's not going to really simplify anything because that impedance would just be R1. So it's already only one element. So for my diagram, I'm going to start in the bottom left. I have here my voltage source with a value of Vs. And I will use the given direction of current that we're assuming that it's going to be clockwise in this system. We're going through, again, I'll just leave this as a resistor, and then we're going to come down and we go through an impedance block of Z, and then we come back to our starting point and we are interested in this V out. And we have some current I will assume is clockwise. I'm going to need to define this impedance Z as I go through in my equations here, but I've able to simplify the diagram a little bit from what was given by turning the resistor and capacitor in parallel into this impedance block. Now we can go and start to write some equations. So we are after V out as the transfer function output, or VO, and Vs as our input. So let's start writing some equations and keep in mind what we're ultimately after. So equation-wise, we can do a KVL equation where I'm going to start in this bottom left and go around the loop and see what all of the voltage gains and drops are as I go through. So again, this will be from a KVL. So I know that it has to add up to 0. I cannot have a net positive or negative voltage as I go around the loop and end up at the same point. So I'll start at the bottom left, and I will go across my source voltage. So I'm going to be traveling with my current. I'm going with the current, and I'm going from the negative to the positive side of the terminal, so I'm going to add Vs. Right, now I will go across the resistor and end up over here. I'm going with the current, and I'm going across my element, so I'm going to have a voltage drop, so that's a negative, really the impedance, R1, or the resistance in this case, times my current, which is I. I'm going to go across this impedance block. So again, I'll have a voltage drop because I'm going with the direction of current. So that has an impedance of Z times the current going through it is I. And then I am going to end up back where I started, so I have closed my loop. So this is my first equation from using KVL. So let's track here our outputs and our, in this case, just one input. So input, we have Vs, the source voltage, and our output so far is the current I. So nothing yet is complete. We have one equation for one output, but it's not the output that we ultimately want, which is Vout. So we can do here a nodal voltage drop to get a second equation. So I can say that the voltage drop across the impedance block is the same as going through Vout. So negative Vo equals negative Z times I. So again, it's negative because this Vout we're going to assume is going to have that same polarity, negative on the bottom, positive on top. So we drop by V naught as we go from the top of Z to the bottom of Z. And then the voltage drop is going to be, since we're going with the current, if we go from the top to the bottom, it's going to be negative Z times I. Now, like we see before, the negative signs are going to drop, so I'll just get rid of them for simplicity here. So V0 or Vout is Zi. So we have a second output added, Vo. Now we have this Z, this impedance block. We need to calculate it because we were not given that as a parameter in the original system. We were given R and C. We were not given Z. So I'm going to add a third equation here where I am going to define Z. So Z is, it's two elements in parallel, so it's going to be the harmonic average of the two, which is 1 over the sum of the reciprocals of the impedances. So I can write that as 1 over, so the impedance of the resistor is going to be R, so 1 over R is going to be the reciprocal of it, plus the impedance of the capacitor is going to be 1 over C times S. Therefore, its reciprocal is just C times S. It's not in the best form yet. I am going to rewrite it in a moment. I want to go back to the first equation just as a note here. The impedance, or the voltage drop, was negative Z times I. The S's are going to come from the definition of Z. So we treat it again basically just like we would resistance, where it's Z times the current, and then we figure out what Z is, which I'll do now down below. 3, I'm going to just rewrite this a little bit instead. So what I'm going to do is I'm going to multiply the top and the bottom of my original Z by R. Because I'd rather, it's not a big deal, but I would rather not have that R in a fractional form in the denominator of Z. But it's not terrible if a parameter is in a fraction. We just don't want S's in fractions. Okay, so the numerator, R times 1, is just going to be R. And then the denominator, I am going to have, here I want things in the descending order of S already, as going to be nicer. So I'll have an R times a C times S plus 1 over R times R leaves us with 1. So again, just rewriting Z in this form. And I'm going to add, again, it's not quite an output, but we'll see we want to eliminate Z in our equation. So I'm going to add that to the output side in that we don't want it on the right-hand side anywhere. We want to substitute it out. So this will help us, again, keep track of how many equations we need and what we're going to tell Mathematica to do if it is how we're going to be doing the algebra part. So I have 1 and 2 and 3a, and I have 3 outputs, I have 1 input. So now let's get our transfer function. So let's transcribe these into Mathematica. So the KVL equation, I'll call KVL1, we know is 0, is this Vs minus R1I. I'm using lowercase I here because capital I would be the square root of -1, so I don't want to use that, minus Z times lowercase I. Okay, that's our KVL equation. Then we have that voltage drop equation. I'll just call it EQ2 here. And this tells us that V out equals Z times I. And then we have that third equation, which is defining what is Z in terms of those given values, the given parameters. So Z equals, double equals, I'll call this EQ3 here. So Z equals that R over RCS plus 1. Notice here also my C is lowercase. If I just have C and I don't have like C1 or C2, I want to use a lowercase because capital C is reserved for the built-in speed of light in Mathematica. So lowercase c. All right, so those are my 3 equations I need, and remember those 3 outputs, which I'll track in a second. So I'm ready to solve. I have KVL1, EQ2, EQ3. I want to solve for my 3 outputs, lowercase I, VO, and Z. So again, Z is not an output per se, but it's going to make sure it's not on the right-hand side of my equations. All right, and clean that up just a little bit there. All right, so we've solved for I, for VO, and, well, Z. It really gives us back where we started, but you'll notice that now Z does not appear on the right-hand side of the I equation or the V out equation. So in that sense, we've accomplished what we wanted. All right, so transfer function. Now I wanted V out over VI, VO over VS. So I'm going to copy this. It's already in a pretty good form. But I'm just going to make sure, I need to get rid of the VS there since the transfer function is VO over VS. Now I have the transfer function correct. And really it is already in the form I want it, but just to make sure, I'm going to do the collect TF numerator, TF, and the denominator. And I'll overwrite TF with that. All right, so again, really didn't change anything, but it gives me, make sure I'm in the form that I want to be, where I'm grouping my coefficients in front of S. So I'll take this and I'll finalize this example. All right, not too much cleanup to do, but I now have my G is V out over V source, or VS, equals, and now I just want to transcribe what I just found. But again, in descending orders of S is the only real difference here. So I have an R1, C times S plus R plus an R1. I'll put them into parentheses there just to remind me that those 2 terms are my constant term in the denominator. So if I were to put this into MATLAB, that R plus R1 goes into that constant spot. And then this is my final transfer function in the form we want it, descending powers of S. To recap how we got to our transfer function, we'll go back to where we started. So we had our circuit here. We had a little bit of a complication because we have a resistor and capacitor in parallel. So what we can do is make an equivalent impedance block with an impedance I am calling Z. So it's going to be a little bit simpler to analyze, but we have to make sure that we have our definition for what that impedance is as we solve our problem. Now the circuit diagram looks fairly simple, like ones we've seen before. We have one element, and we're trying to find the voltage over a second element. So I chose to solve this one using 1 kVL equation, and then the voltage drop across the impedance block, which was ultimately the voltage that we want to find, that Vout. And I had to add a third equation that defined what that impedance Z was. In this case, again, I have two elements in parallel with each other, so the impedance is their harmonic average, which is, in this case, 1 over the sum of their reciprocals. So the impedance of the resistor was R, the reciprocal 1 over R. The impedance of the capacitor is 1 over Cs, and its reciprocal then is C times S. I could have left Z looking like this, but I'd rather get rid of denominators in my fraction itself. So I multiplied top and bottom by R, which is the same as multiplying by 1, and I'm able to rewrite Z as this R over RCS plus 1. Equations 1, 2, and 3a I then put into Mathematica to eliminate I, V, out, and Z, or really to solve for them and make sure that none of them were on the right-hand side. And from there, I was able to get my final transfer function V out over Vs in the proper form, descending powers of S, and it's in terms of just the given parameters R, R1, and C.